Hello class, and welcome to today's algebra lesson, which is about operations with radical expressions. By the end of today's lesson, you will be able to add, subtract, and multiply radical expressions, as well as use conjugates to rationalize denominators. So the first thing we want to pay attention to when we are doing these radical operations is we want to know that these radicals can be treated like variables. So for example, when we had the variables 4x plus 2x, those were like terms. Those were things that we could put together and say that we have a total of 6 x's. If you have like radicals, so 4 square roots of 5, and you're adding on another 2 square roots of 5, you have 6 square roots of 5. So we treat them like variables, where if we have the like terms, we can put those things together. Same thing happens if we had unlike variables. 4x plus 2y simplifies to just 4x plus 2y. We can't actually put those pieces together because the first one is a group of x's and the second one is a group of y's. Same thing would happen with radicals. 4 square roots of 5 plus 2 square roots of 3 can't be combined because these two radicals are different. So starting with this one here, we've got 10 square roots of 7 plus 5 square roots of 13 minus 4 square roots of 7 plus 6 square roots of 13. So we want to look for those like radical terms. In this case, 10 square roots of 7 subtracting 4 square roots of 7 gives us 6 square roots of 7. And then the other like term is 5 square roots of 13 plus 6 square roots of 13, giving us 11 square roots of 13. We cannot combine this any further because 7 and 13 are not like radicals. Go ahead and try this one on your own. So for this, all three of our radicals are like, so I do 5 plus 7, which gives me 12. Subtracting 6 gives me an answer of 6 square roots of 2. Sometimes in order to be able to do the addition and the subtraction, we have to simplify the radicals first. So this is combining today's lesson with the last lesson. So when I look at 2 square roots of 18, I know that 18 can be divided by a perfect square. So it's actually 2 square root of 9 square root of 2. Minus, I also can simplify 32. So I've got 5 square roots of 16 square roots of 2. And I also can square root or simplify 72 to 36 times square root of 2. You could also have broken it down into 8 and 9, but 8 then would get split into 4 and 2. So there's a couple different ways you could split up square root of 72. Now I need to actually solve these pieces. So the square root of 9 is 3. 2 and 3 gives me 6 square roots of 2 in the front. The square root of 16 is 4. So minus 5 times 4 is 20 square roots of 2. And then I've got the square root of 36, which is 6 square roots of 2. So I do 6 minus 20, which is negative 14, plus 6, which gives me negative 8 square roots of 2 in its most simplified form. So again, to start, if your square roots don't match, you want to check if you can reduce them at all so that we can get them to like radicals. Go ahead and try simplifying this one on your own. So 45 splits into 9 and 5, 20 into 4 and 5, and 245 into 49 and 5. Once we do that, we've got 9 square roots of 5 in the front plus 2 square roots of 5, which is 11, subtracting 7 square roots of 5, giving you 4 square roots of 5 as your simplified answer. Switching over to multiplication, once again, we treat radicals like we would treat variables. So in this case, we would multiply our numbers. So 3 times 5 gives us 15. And then x times y is just xy. When we come down to the radicals, the piece that is slightly different is everything that is outside the square root. So in this case, the 3 and the 5 gets multiplied and stays outside the square root. And then everything inside the square root. So in this case, x and y get multiplied and it's inside the square root. If I did one more example here, just to show what I mean by inside and outside, if I did, for example, 4 square root of 2a times 7 square root of 3b, 4 and 7 are on the outside of my square root. So I'm going to multiply those and I get 28. And then inside my square root now, I have 2 times 3, which is 6, and then a and b, since those are being multiplied. So it could be numbers inside, it could be numbers outside. It could be variables inside, it could be variables outside. The key piece is that whatever is under the square root stays under the square root to start. Whatever is outside of the square root stays outside of the square root. So when I have this problem here, I'm going to start with my outsides. 7 times 2 is 14. And then insides, 2 times 6 gives me 12. We always want to check for simplifying. 12 can be divided by a perfect square. So I've got 14, square root of 4, square root of 3. The square root of 4 can be solved. So that is a 2 now. So I've got 2 times 14, which gives me 28 square roots of 3 as my simplified radical form. Go ahead and try this one on your own. We start with 9 times 11, so 99, and then 15 times 5 is 75. That can be broken down into 25 and 3. Square rooting gives you 5, so 495 square roots of 3 is our most simplified form. We can also distribute, just like we would with regular multiplication with variables. We can do a distributive property where we are doing multiple multiplications. You follow the same rules. We multiply the outside first. So 3 times 2 gives us 6. Inside the square root is 5 times 5, or 25. Then we jump to the second part, plus outsides 3 times 5 is 15. Insides 5 times 3, once again, gives us 15. The square root of 25 can be solved, so that's going to be 5, leaving us with just 6 times 5 in the front, or 30, plus 15 cannot have a perfect square factor, so we leave it as just 15 square roots of 15. You cannot add 15 plus 30 because the 15 is being multiplied by the square root of 15. In order to be able to add, you'd have to solve the multiplying first, which we cannot, and then move on to the adding. So when you end up with this right here, you do not add the 30 and the 15 because they are not like terms. One more example of this distributive property. So for this first part, I've got 8 times. There's nothing in front of this square root, so you can always put the 1 there as your placeholder. So 8 times 1 gives you 8, and then insides, square root of 7 and square root of 3 is square root of 21. Plus, once again, distributing to your outsides first, so 8 times 6 is 48. 7 times 2 is 14. The square root of 21 cannot be divided by a perfect square, and neither can the square root of 14. So sometimes after you distribute, that's as simplified as it can go, because we cannot break it down to add or simplify these two different radical pieces. Go ahead and try this one on your own. Starting with the outside, we get 12, and then the inside, square root of 6. Then we distribute again, 18 square roots of 4. We can solve the square root of 4 to 2. So then we have 18 times 2 is 36. Once again, you cannot add these together because 12 has multiplied by the square root of 6. 36 does not have a square root anymore. The conjugate. This is going back to a piece from yesterday when we were talking about rationalizing denominators. Remember, one of our rules for simplifying things is there cannot be a square root in the bottom. Conjugates are used when there is a square root and also adding or subtracting. A conjugate, by definition, is two square roots or two groups of square roots with opposite signs. The point of a conjugate is that it can cancel out to eliminate the square root. So essentially, we go back to our box, and I've got 2 with a positive square root of 7 and 2 with a negative square root of 7. When I multiply these things, I end up with 4, and then positive 2 square roots of 7, and then negative 2 square roots of 7, and then a negative square root of 49. The way that this eliminates our square roots is positive and negative cancel each other out. So these factors are always going to cross out. So I'm going to have 4 minus the square root of 49, which is 7, giving me a final answer of negative 3. So if you want to draw the box every single time to make sure you do your conjugates correctly, you can. Or you can take the shortcut, which is to write it out as 2 squared, or whatever number is in front squared, minus the square root of the 2 numbers multiplied. So you can skip the middle 2 boxes. When you do that, once again, it's still going to give you 4 minus 7, which still gives you the answer of negative 3. So when you are using conjugates to solve, you can either write out the full box, or you can take a shortcut on this one because the middle 2 pieces will always cancel out. Go ahead and find the numerical value of the conjugate for these 2 on your own. So we've got 5 squared minus 6 times 6 is 36. So 25 minus 6 gives us a conjugate value of 19. So how does this actually help us solve problems? When we have the fraction with the square root in the bottom, along with addition or subtraction, we're going to multiply both the numerator and the denominator by the conjugate. So in this case, the opposite is 5 minus square root of 2 and 5 minus the square root of 2. So in the numerator, it becomes a distributive property. 3 times 5 is 15. 3 times the square root of 2, so a 1 in front, gives us minus 3 square roots of 2. Those again cannot be combined because the 15 doesn't have a square root. In the denominator, we do our conjugate math now. So 5 squared minus 2 times 2 gives us the square root of 4. So I end up with 25 minus 2, or 23. So this is as simplified as this fraction can go. There is no longer a square root in the denominator. It has now been moved to the numerator. Go ahead and try this one on your own. So our conjugate this time is 4 plus the square root of 3. So when we do that multiplication, you end up with 4 squared, which is 16, minus the square root of 9, which is 3. 16 minus 3 gives you that 13. And we end up with 28 plus 7 square roots of 3 over 13. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.